Well, hello and welcome back to Distributions, Part 2. So we'll begin with some multiple choice questions about the difference between a population and a sample. In our previous look at distributions, we were dealing with populations. We had all the data and we simply wanted to see where individual people landed against the whole population. So we were dealing with population data. Data is based on all the members of a specified group, for example, all COB students. And population data is described by parameters, which are numerical values that summarize the data. And they have Greek letters, which you saw. So you had mu, which is the mean, sigma, which is the standard deviation, and sigma squared, which is the variance. Now we're going to be dealing with statistics. And with statistics, there's an analog for each of these. So for mu, we have x bar, which is the average of the sample. Instead of sigma, we have s, which is the standard deviation of the sample. And instead of sigma squared, we have s squared, which is the standard, which is the variance of the sample. So sample data is data that's based on a subset of members of the population, specified group. So COB students in this class as opposed to all COB students. And statistics are numerical values that summarize the sample data. And that's always designated by English letters. So population, sample from the population. All right. Of the US population, 36% has an allergy. A sample of 1,200 randomly selected adults resulted in 33.2% reporting an allergy. What's the population? Well, the population is US adults. So all adults in the US, B. What's the sample? 1,200 randomly selected adults, D. And 33.2% is a sample statistic. And 36% is a population parameter. What's the correct interpretation of variance? Well, variance is the squared standard deviation. So look for the one that's talking about squared units. And it looks like it would be A. And what's the correct interpretation of the standard deviation? That's going to be B, average difference from a data point to the mean. What does simple mu represent? It's the population mean, B. And what does the symbol sigma represent? The population standard deviation, which is D. Okay. In our next tab, we have that sample means cluster closer to the true population mean than individual values. As a result, the probability of a sample mean deviating from the true population mean is lower. So we're actually going to see this. We're going to revisit a problem that we did in the prior unit with Ralph in the ACT exam. So Ralph takes the ACT exam. So the N is 1 because it's just Ralph. And we're after his percentile, so it shades left. Population mean is 21, average score in the ACT, and the standard deviation is 3. He scores a 20, and so now we calculate his z-score, which is x minus mu divided by the standard deviation. And the probability of that score equals norm dot s dot dist. %. Okay, so he's in the 36, almost 37th percentile. So he's slightly below average at a score of 20. Now let's see what happens if we have a sample. So let's say Ralph is among 30 students sampled at random that take the ACT. So there's 30 of them. Still left. Mu is still the same. It's 21. Sigma is standard deviation of 3. But, and this is the one thing that changes here between these two. Here's the difference, right? That for the expected variability, we don't just take sigma. We take sigma, which is 3, equals 3, divided by the square root of n, which is here 30. So we get a much lower expected variability. Because before it was 3, now it's like 1/2. Alright, x bar is 20, so it's going to be the same. With the average of the group, same as the average for Ralph. But the z-score is also going to be very different. So equals x minus mu divided by this new expected variability. So a much more extreme z-score, from negative 0.33 to negative 1.83. And that's going to result in a much lower probability. So equals norm dot stop dist. .4%. And you can see this here on the graph. So here's Ralph. He's in the 36, almost 37th percentile. But that group of people that also got, the whole group averaged to the same score of 20 that Ralph got, there would only be a 3.4% chance that that would happen. In other words, it's really, really, really unlikely that a group of people, a group of 30, who take the test are going to deviate from the standard, from the mean, by a score of even 1, right? All we're doing, if you think about it, was going from 21 to 20, right? I mean, even going that little bit down puts you in a really low percentile. It just doesn't happen often. And it's that insight, which is why sample data can be used to test hypotheses, because the likelihood of getting a sample, if your sample size is pretty big and it's a random sample, the likelihood of getting a sample that deviates from the mean by even a relatively small amount is really unlikely, right? Things tend to cluster around the mean. All right, so let's answer these questions on here. Only one formula changes between P of x and P of x bar. What is it? It's the expected variability. Which has the lower variability? It's P of x bar. She just said that. Which is more representative of the population? Well, sample average. Much closer to the population average. How does the calculation of variability change? Sigma is reduced by a denominator. We divide it by the square root of n. A larger denominator leads to a smaller expected variability. A smaller expected variability leads to a more extreme z-score, and a more extreme z-score leads to a smaller probability. Compare the raw scales in each graph. Raw x bar grows. Here's raw x bar. Grows much more slowly. See how the scale's going up? much more slowly than raw x. Okay. Now we look at the central limit theorem using cookie jar. So imagine you have a big jar filled with different sized cookies, different sizes. Some are small, some are medium, some are large. You want to figure out the average size of a cookie in the jar, but instead of measuring all the cookies, which would take forever, well, maybe not, but you know what I mean, you decide to do it by taking small handfuls or samples of cookies and measuring them. Here's how it works. Take a sample of 4 cookies, record their sizes. Calculate the average size for that sample. Repeat this many, many times, always picking 4 cookies and calculating the average for each sample. Plot the averages from your samples on a graph, and that graph would look like this. So each of these X bars represents a sample of 4 cookies. And as you can see here, the samples closer to, there's more samples come out closer to the mean than really far away from the mean. So for example, really far away from the mean, that would be a sample that had only little cookies, and really far away from the mean on this side, it'd be a sample that just managed to have only big cookies. You know, in most cases, you can get samples that have mixed cookies, and so the average is going to be in here. So even though the individual cookie sizes are all over the place, some are low and some are high, the averages from your sample, right? These are the averages, tend to form a nice smooth bell-shaped curve, which is a normal distribution. The more samples you take, the more this bell shape becomes clear, and most importantly, the center of the bell shape is the real average cookie size for the jar, even if you measure all of the cookies. So in other words, this is the real average size right here, whatever this is. I mean, we're showing z-scores, so we don't have the raw values. But this is the true average size of a cookie in the jar, just based on the sampling distribution. The central limit theorem tells us that even if individual things, cookie sizes, are random, the average size from samples will be predictable and normally distributed as long as you take enough samples. This is why it's so powerful and widely used in statistics, science, and everyday data analysis. In other words, we can accurately predict that we're going to get this nice bell-shaped curve. And that's important because it also tells us that these things in the tails are very unlikely, which is how we do hypothesis testing. We say, hey, we got a sample, and based on the sampling distribution, it's really unlikely, so we think that we're going to reject the null hypothesis. But more on that, obviously, in the next unit. If you took larger samples, say 30 cookies at a time, then each of the sample averages would be even closer to the real average cookie size in the jar. You would still have a bell-shaped curve, but it would be more tightly clustered around the true average because larger samples reduce variability. This is one of the key insights of the central limit theorem. While every sample mean in the distribution is technically possible, extreme averages in the tails are far less likely, occurring less than 5% of the time. Imagine another distribution overlapping ours with its center positioned over the tail of our distribution. You can see this here, the two distributions overlap. a sample mean falling in that tail would be more consistent with the, oops, let me undo that, would be more consistent with the other distribution than with ours. So in other words, a sample out here in the tail was actually really close to the mean of this distribution, so we might be tempted to say, hey, maybe that sample doesn't really belong to our distribution, it belongs to the other one, which would mean rejecting the null hypothesis. In hypothesis testing, the null hypothesis assumes the sample comes from our original distribution. If the sample mean falls in the tail region, we have evidence that it's unlikely under the null, and we reject the null hypothesis. And there you have it. That's our unit. Thank you for joining us. Goodbye.